Hello everyone, welcome to our channel Radioactive. So today we are going to discuss a very interesting and important topic, radioactivity. So without any delay, we are going to discuss what we will discuss in this topic. So in this topic, we will discuss first history of radioactivity, then what is radioactivity, introduction about radiations, type of radioactivity, law of radioactivity, decay constant, mode of radioactive decay, half-life, mean life, and radioactive equilibrium. In this topic, we will also cover these questions. First is define radioactivity and its unit. What is the difference between natural and artificial radioactivity? Then describe law of radioactivity where we will describe decay constant. Describe mode of radioactive decay. There we will discuss about alpha, beta and gamma decay, electron captures, internal conversion, isomeric transitions. Explain half-life and mean life. Define radioactive equilibrium. Is in this topic we will also discuss or cover these questions. So first of all, history. Radioactive decay, also known as nuclear decay, radioactivity, radioactive disintegrations or nuclear disintegration. So what is the radioactive decay or the radioactivity? Is the process by which an unstable atomic nucleus loses energy by radiation. Generally these radiations are alpha, beta or gamma radiations. Okay, so we can say that it is radioactivity is the process of spontaneous decay of alpha, beta and gamma radiations. Radioactivity was discovered in 1896 by Henry Becquerel. Henry Becquerel in 1896 observed uranium salt emits rays. That uranium salt is phosphorescent uranium salts or phosphorant salt. We can say that these materials glows in the dark after the exposing to light. So that after this discovery of radioactivity, Marie and Pierre Curie contributed to understanding of radioactivity and discover new radioactive elements. These are the radiums and all. So what is radioactivity? Radioactivity is physical phenomena of certain elements such as uranium, thorium, radium, radon and many other elements which are having the heavy nuclei or unstable nuclei of emitting energy in the form of radiation. So what is radiations? To achieve a stability, that means the which nucleus is unstable, to achieve that stable, the nucleus emits particle or electromagnetic waves that is known as radiations. So any nuclear species particulate configurations of proton, neutron and energy that exhibits radioactivity are known as radioactive nuclei. Radioactivity is unaffected by the physical condition, that is temperature, pressures and electric or magnetic field. So we can say that the radioactivity is unaffected. That means these temperature, pressures and electric or magnetic field is not going to affect in the process of radioactivity. So that we can say that simply we can say that radioactivity is that the unstable nuclei, to make it stable, it emits some radiations. Okay, that is process is called as radioactivity. So here briefly introduction about radiation. What is radiation? Radiation is the emission and transmission of energy through a space or matter in the form of wave or particles. Types of radiation. There are two mainly types of radiations. One is ionizing radiation. Second one is that non-ionizing radiation. In our application, we mostly look about ionizing radiation. So there are two types of ionizing radiation. One is in direct ionizing radiation. Second one is that indirect ionizing radiation. Direct ionizing radiation, that is charged particles which are electrons, protons, alpha, beta. This type of radiations are direct ionizing radiation. Second one is that indirect ionizing radiation, that is neutral particles which are photons, x-rays, gamma rays, neutron. These are indirect ionizing radiations. Second one is that non-ionizing radiations. Non-ionizing radiation, that means there is visible light, or the in electromagnetic spectrum we can say that we are having the less energy than the UV rays, that is non-ionizing radiations. Mostly it is visible light. So next one is that types of radioactivity. So there are two types of radioactivity. First one is that natural radioactivity. Second one is that artificial radioactivity. Natural radioactivity, that means these are the elements that uranium, radium, these are naturally occurred. These are the naturally unstable nuclei or the unstable elements. to make their stable conditions or the stable nucleus, it emits some energy in the form of radiations. This happens naturally, so it is called as natural radioactivity. And second one is that artificial radioactivity. So like cobalt 59, this having the this cobalt 59 is naturally stable. To make it unstable in the nuclear reactors, we are putting or bombard or neutrons in cobalt 59 to make it unstable. After that, it will be make cobalt 60, and it emits some energy in the form of radiations. So it is this type of radioactivity is called as artificial radioactivity. So here is some difference between natural radioactivity and artificial radioactivity. Natural radioactivity, emission of radiation due to self disintegration of nucleus, and artificial radioactivity, emission of radiation due to the disintegration of nucleus through the induced process. And the second difference is that alpha, beta, and gamma radiations are emitted in the natural radioactivity, and in artificial radioactivity, mostly elementary particles such as neutron, positrons, etc. are emitted. And in natural radioactivity, it is a spontaneous process, or spontaneous process, that means those processes which happen spontaneously. Okay, in artificial radioactivity, it is an induced process. Naturally, radioactivity exhibits by element which atomic number is more than 83, and artificial radioactivity generally exhibits by the element with atomic number less than 83. Naturally radioactivity, these cannot be controlled, and artificial radioactivity, this can be controlled. These are the some difference between artificial radioactivity and natural radioactivity. Law of radioactive decay or the radioactivity. Rutherford and Soddy study on the different kind of radioactive nuclei and gave a law called as law of radioactivity. The radioactivity disintegrations or the radioactive disintegrations is a spontaneous process, so it is independent of chemical and physical process. Radioactivity is a random process. We can say that it is impossible to predict that which atoms will be disintegrated first or the last, and also unable to predict when a particular nuclear will be decay or disintegrated. So decay constant. The decay constant that is represented by minus lambda is a fundamental parameter in a study of radioactive decay. Here is a minus sign represents the decay or disintegrations. It is described the probability that a single atom of radioactive substance will decay per unit time. It is characteristics constant for each radioactive isotopes. The number of atom disintegration per unit time, that is dN by dt, is the proportional to the number of radioactive atom, that is n. So mathematically it is represented dN by dt is directly proportional to the n. So the above proportional change to an equation by the inserting the disintegration constant, that is dN by dt is equals to minus lambda n, where the minus sign indicates the rate of disintegration decreases with times. Also we will rearrange these equations in a form of dN by n is equals to minus lambda dt. After that we will integrate these equations with both sides in a limitations of n naught to n, dn by n is equals to minus lambda dt. In minus lambda is outside of this integration because it is constant. So that dn by n having integration, that is log n in limitations of n naught to n is equals to minus lambda t, limits of t0 to t. So that log n minus log n naught is equals to minus lambda t. After that this minus will be equals, we know that log first minus second is equals to log first by second, that means log n by n naught is equals to minus lambda t. So n by n naught is equals to e to the power minus lambda t. So that this equations rearranging in this form, n is equals to n naught e to the power minus lambda t, where n naught is initial number of radioactive atoms, that means it is the number of radioactive atoms at zero decay. The above equation shows the law of radioactive disintegrations or law of radioactivity. Next one is that activity. The rate of disintegrations dn by dt is also called as activity. Mathematically, we can write that A is equals to minus dn by dt is equals to lambda n. That minus sign indicates disintegration. So, n having the value of n is equals to n naught e to the power minus lambda t. So, we write that A is equals to lambda n is equals to n naught e to the power minus lambda t. So, we are putting this value to here. So, there is lambda n naught is equals to a naught. So we can write that A is equals to A naught e to the power minus lambda t, where A naught is initial activity or activity at time 0, and A is the activity after time t in the above exponential equations. The next one is half-life. The time in which radioactive substance remain 50% of its initial concentration is called half-life time. Okay, that means radioactive substance loses their activity of the 50% or half. It is called as half-life time. Okay, the phenomena of half-life time is introduced by Rutherford. Mathematically, we will discuss the half-life from the law of radioactive disintegration, that is n is equals to n naught e to the power minus lambda t. For half lifetime, the time will be t half, and n is equals to n naught by 2. So that n naught by 2 is equals to n naught e to the power minus lambda t half. So that e is equals to minus lambda t half is equals to 1 by 2. So next, e to the power lambda t half is equals to 2. Taking natural log both side, we get log e to the power lambda t half is equals to log 2. So lambda t half log e is equals to log 2. So after that, this lambda goes this side. So t half is equals to log 2 by lambda, and this is also log e. So like directly we put the log 2 value, that is 0.693. So that is t half is equals to 0.693, or we will also write like this. So t half is equals to log 10 base 10 2 into 2.303 by lambda. So 2.303 into 0.3010 by lambda. So that is the value of log base to 2 value. So that is, after multiplying this, we get the half-life value or half-life time equations, that is t half is equals to 0.693 by lambda. This is the equations for half-life time, where lambda is the decay constant. So next one is that mean lifetimes. The mean lifetime or average lifetime, that is represented by TA, where A represents average time, is the average lifetimes for decay of radioactive atoms. It can be shown that TA is equals to sum of lifetimes of all atoms by total number of atoms. So mathematically, we will discuss mean lifetime or average lifetime. If dt is very small, then each of dn atom have lifetime t. Okay, so lifetimes of all dn atom is equals to t dn. We can write that. So that ta is equals to integrations with limitation of 0 to lambda t dn by n naught. This is equation first. So from the law of radioactive disintegration, that is n is equals to n naught e to the power minus lambda t. We will mathematically, so differentiating both side of law of radioactivity or law of radioactive disintegration, that is dn is equals to n naught minus lambda e to the power minus lambda t. So after putting this value dn in equation 1, we get ta is equals to integration with the limitations of infinity to 0 t n naught minus lambda e to the power minus lambda t by n naught. So that we are changing this limitations of this integrations, that is ta is equals to lambda just outside, and integrations of the limitations is that 0 to infinity, that t e to the power minus lambda t dt. This minus sign will be changed by the changing the limitations of this integrations, and lambda is outside of this integration because it is constant. So that ta is equals to lambda t e to the power minus lambda t by minus lambda with the limitations of 0 to infinity minus integrations 1 e to the power 1 into e to the power minus lambda t by lambda minus lambda dt is equals to, so that this term will be 0. So that is here this term will be 0. So here 0, and this lambda is outside, so that lambda by lambda, that is minus e to the power minus lambda t by minus lambda with the limitations of 0 to infinity, and the lambda will be crossed by 1. So that, and after that this lambda is outside, so that is minus 1 by lambda e to the power minus lambda 0 to infinity is equals to minus 1 by lambda 0 minus 1, because of 0 e to the power 0, that is 0 e to the power infinity, that is 1. So minus lambda 0 minus 1, so minus minus it will be plus, so that is 1 by lambda. Ta is equals to 1 by lambda. This is the equations for mean life or average lifetime. So next is relation between half-life and mean life. Half-life is equals to 0.693 by lambda, and the mean life or the average life is equals to 1 by lambda. So lambda will be equal. So we will write that 0.693 by t half is equals to 1 by Ta. So that Ta is equals to t half by 0.693. So 1 by 0.693 is 1.44. So Ta is equals to 1 by 1.44 of t half. That means the average life is equals to 1.44 times of T half. Unit of radioactivity, SI unit of radioactivity or activity is becquerel. 1 becquerel is equals to 1 dps. Dps, that means disintegration per second. But nowadays commonly used the unit is curie. So we can say that the curie is the another unit of radioactivity. So the relation between the becquerel and curie is 1 becquerel is equals to 3.7 into 10 to the power 10 becquerel. Okay, so there is also another unit of radioactivity, that is Rutherford. 1 Rutherford is equals to 10 to the power 6 becquerels, or we can say that 1 Rutherford is equals to 1 mega becquerels. So unit of decay constant is per unit per times. Okay, also it may be time, that means it will be per second, per hour, per day, or per years. In all terms we will find that radioactivity. Mode of radioactive decay. So there are different possible mode of nuclear decay or radioactive decay. Commonly that is alpha particle decay, beta particle decay, and gamma decay or gamma emissions. In alpha particle decay there is alpha decay, and in beta particle decay there is beta plus decay, beta minus decay, and electron captures. In gamma decay there is gamma decay and internal conversions and isomeric transitions or internal pair conversions. So alpha particle decay or alpha decay is a type of radioactive decay in which an unstable atomic nucleus release an alpha particles. Alpha particle, that means helium particles with having the 4 nucleus, that means the mass number will be 4, and the consisting of 2 protons and 2 neutrons, that means the atomic number will be 2. This process helps the unstable nucleus achieve a more stable configurations. So that alpha particle typically occur in the heavy element like uraniums, radiums, and like thoriums. Alpha particle is that consist of 2 proton and 2 neutron, that is symbolized by heliums or the alpha helium 2 force. So there is X is that parent nuclei with having atomic number Z and mass number A, and it is Y, that is equals to Y. Y is that daughter nuclei with atomic number Z minus 2 and mass number A minus 4, and plus helium particles. Okay, helium 2 force. There is some examples: uranium 92 238 is equals to thorium 92 234 plus helium particles or the alpha particles. Here is also some energy, so there is plus q. Beta particle decay. Beta decay is a type of radioactive decay in which a neutron is unstable nucleus transformed into protons or vice versa. That means the neutron will be transformed in protons or proton will be transformed in neutrons in a nucleus. So that resulting in the emission of beta particles. The beta decay can occur in the two forms: beta minus decay and beta plus decay. So like X is that parent nuclei and Y is that daughter nuclei. X having Z A, then A having Z minus 1, there will be the beta plus decay, and Z plus 1, there will be the beta minus decay. There is no change in mass number, that means A. Beta minus decay. So what happened in beta minus decay? In beta minus decay, a neutron in unstable nucleus is converted into proton. That means neutron will be converted into proton in beta minus decay. During this process, the nucleus emits beta minus particles, that is an electrons, and an antineutrino particles, that is symbolized by rho bar E. Okay, these equations for the beta minus decay, that is n to p, n that means neutron, p that means protons, plus electron plus antineutrino inside this nucleus decay into protons and electrons and an antineutrino particles. The atomic number increases by 1 because of neutron turns into or neutron convert into proton, but the mass number remain the same because of neutron and proton have the same mass. Okay, so that example of beta minus decay, consider the carbon 40, so that the parent will be carbon 614 and the daughter will be nitrogen 714 plus electron plus anti neutrino. This type of decay is beta minus decay. So in beta plus decay, what will be happen in beta plus decay? Beta plus decay, that means the proton is an unstable nucleus is converted into neutrons. Here in beta plus decay, proton is converted into neutrons. And what was in beta minus decay? There was neutron was converted into protons. So after in the beta decay, proton is converted into neutrons. In this process, emitting a beta plus particle, that is positrons and a neutrino. Okay, these equations for the beta plus decay, that is proton converted into neutron plus positron plus neutrino particles. Okay, the proton inside the nucleus decay in a neutrons and positrons and a neutrino particles. Okay, the atomic number decreases by 1 because of proton is converted into neutrons while the mass number will be same. So here we will going to take an example of fluorine 18. So that fluorine 18 or fluorine 918 is that parent nuclei and the oxygen 818 is that daughter nuclei or the daughter elements. So that here is we see that there is change in atomic number, there is no change in mass number. Here there is less atomic number by 1. Okay, because of one proton is converted into neutrons. Okay, so that fluorine 9 is converted in oxygen 8, or there is mass number will be same, plus positron and neutrino particle will be decay. So here is the some summarizations of the beta plus decay and beta minus decay. Beta minus decay, the process which the neutron converts into protons, that means atomic number will be gained by 1. There is no change in mass numbers and the particle emits by the electrons and anti-neutrinos. In beta plus decay, proton converts into neutrons. There is change in atomic number by the losing 1, and there is no change in mass number, and the particle will be emit is positron and neutrino. So next one is that gamma decay or gamma emissions. Gamma decay is a type of radioactive decay in which an unstable atomic nucleus releases excess energy in the form of gamma radiations, that is high energy electromagnetic waves or photons. Okay, the decay typically occur after a nucleus undergoes alpha or beta decay and is left in an excited state. Okay, so the gamma decay allows the nucleus to return to its ground states, the lowest energy, that is the ground state. In these states, the first exciting state to ground state, there is releasing some energy, that is gamma decay or gamma emission. So there is no change in atomic number and also no change in mass number. So like we can see like this is the excited state and this is the ground state. Electron is stable at ground state. When the it is excited, it goes to the excited state. After the coming to the excited state to ground states, by the undergoes process of alpha or beta decay, it emits photons or the gamma rays, that is called as gamma decay or gamma emissions. Electron captures is a type of beta decay. The electron capture is a phenomena in which one of the orbital electron is captured by the nucleus, thus transforming of protons in the nucleus into neutrons. Okay, so that equations is protons 1 1 plus electron minus 1 0 is converted into neutron 0 1 plus releasing some energy. Electron capture is an alternative process to the positron decay. The unstable nuclei with the neutron deficiency may be increased their n by p ratio. Np ratio, that means neutron proton ratio, to gain the stability by the electron captures. The resulting nucleus is still the excited state. The releasing or the releases its excess energy almost intentionally by the emissions of gamma ray photons. The electron capture involves mostly in the K cells electrons. This process is referred as K captures. If it will be happen in L cells, it will be L captures. As a result, electron captures a vacancy is created in the involved cells, which is then filled by the orbital's outer orbit electrons. The electrons transitions can give to characteristic X-ray, also called as fluorescent X-ray. Alternatively, these transitions can cause the ejections of another electrons called as Agar electrons. Internal conversion. Next one is that internal conversion. What is that internal conversion? A nucleus is still left in that excited state after a nuclear transformations may get rid of its excess energy by the emission of a gamma ray or by a process called internal conversion. That means internal conversion is an atomic decay process where an excited nucleus interact electromagnetically with one orbital electrons of an atom. So this will be cause the electron to emit or ejected from the atoms. Okay, so in internal conversion process, the excess nuclear energy is transferred to one of the orbital electrons, which is then ejected from atoms, analogous to the internal photoelectric effect, in which gamma photons escaping from the nucleus interact with an orbital electrons of the same atoms, so that the kinetic energy of the internal conversion electron is equal to the energy released by the nucleus minus the binding energy of the electron cells from which the electron is ejected. Okay, so the minus nucleus minus the binding energy, that means the energy need to be break the bind or the binding. Okay, next one is isomeric transitions or nuclear isomerism. It is also a types in gamma decay or gamma emissions. Okay, in this case, some of the nuclides, the excited nuclear state following the emission of alpha or beta particle persist with a finite half-life. In that case, the nucleus is said to exist in the metastable state before decaying into the ground states with the emission of gamma ray or internal conversions. Okay, that means it is a radioactive decay process that occurs in an atom where the nucleus is an excited or metastable state. Okay, like following the emissions of alpha or beta particles, like the same. Okay, there will be the extra energy in that nucleus is released by the emission of gamma ray. Okay, to the returning the nucleus to the ground state. Okay, so the transition from the metastable state to the ground state is called as isomeric transitions. Okay, the metastable nucleus is an isomers of the final product nucleus. Okay, isomeric nuclei have the same atomic and mass number but different their states of energy. Okay, so the isomeric transition does not involve change in the proton or neutrons. Okay, so an isomeric transition result in either gamma emissions or internal conversions. Okay, so there is also internal pair conversion. So next point is radioactive equilibrium. What is radioactive equilibrium? The condition of constant ratio of parent and daughter activity is called as equilibriums. If it is happen with radioactive elements, that is radioactive equilibriums. Okay, so it is also shows the relation between parent and daughters. When the radioactive equilibrium will be exist, when the half life of daughter is smaller than the half life of parent, then only the equilibrium will be exist. Okay, when the half-life of daughter is greater than the half-life of parents, there is no equilibrium, or the no radioactive active equilibrium will be exist. Okay, so radioactive equilibriums is divided in three parts. One is ideal equilibriums, second one is that secular or permanent equilibriums, third one is that transit equilibriums. We will discuss one by one. First one is that ideal equilibriums. What is ideal equilibrium? So that when the activity of parent and daughter are equals, this situation is called as ideal equilibriums. So in this case, the situations must exist at same moment t is equals to tm. So mathematically, we will see we have t is equals to tm, that is lambda 1 n1 is equals to lambda 2 n2. But dn2 by dt is equals to lambda 1 n1 minus lambda 2 n2. But lambda 1 n1 is equals to lambda 2 n2, so it will be 0. So that dn2 by dt is equals to 0. n1 is equals to n0 e to the power minus lambda t. So at t is equals to tm's, activity of point A is lambda 1 n1 lambda 1 n0 e to the power lambda 1 tm. This is equation 1. So the Tm is equals to 1 by lambda 2 minus lambda 1 into natural log lambda 2 by lambda 1. So this will be lambda 1 n1 is equals to lambda 1 n naught e to the power minus lambda 1 into 1 by lambda 2 minus lambda 1 with natural log lambda 2 by lambda 1. So after simplifying this, we will get lambda 1 n1 is equals to lambda 1 n naught e to the power minus lambda 1 lambda 2 minus lambda 1 into natural log lambda 2 by lambda 1. So it will be lambda 1 n1 is equals to lambda 1 n naught e to the power natural log lambda 2 lambda by lambda 1 to the power lambda 1 by lambda 2 minus lambda 1. So that lambda 1 n1 is equals to lambda 1 n naught lambda 2 by lambda 1 to the power lambda 1 by uh, lambda 2 minus lambda 1. Okay, so that t1 is equals to 0.693 by lambda 1 and t2 is equals to 0.693 by lambda 2. So the equation will be lambda 1 n1 is equals to lambda 1 n naught t2 by t1 to the power t1 by t1 minus t2. This equation shows the ideal equilibrium. Okay. Second one is that secular or permanent equilibrium. When the secular or permanent equilibrium will be exist or happens if the half-life period of parent isotopes is much larger than half-life of daughter isotopes, then the equilibrium is called secular equilibrium. Okay, that means lambda 2 is much greater than lambda 1. Okay, so mathematically we will see secular or permanent equilibriums. Permanent or secular equilibriums is the same thing. In this parent nuclei, larger lived and daughter nuclei are shorter lived. So here T1 is much greater than T2, then lambda 2 is much greater than lambda 1, or we can also say that lambda 1 is much smaller than lambda 2. So n2 is equals to lambda 1 n naught by lambda 2 minus lambda 1 into e to the power minus lambda 1 t minus e to the power minus lambda 2 t. Let lambda e to the power minus lambda 1 t will be outside. We will get n2 is equals to lambda 1 n naught by lambda 2 minus lambda 1 e to the power minus lambda 1 t into 1 minus e to the power minus lambda 2 t. So that n2 is equals to lambda 1 n1 by lambda 2 minus lambda 1 into 1 minus e to the power minus into lambda 2 minus lambda 1 t. So multiplying by lambda 2 both sides, we get in the previous equations lambda 2 n2 is equals to lambda 1 lambda 2 n1 by lambda 2 minus lambda 1 into 1 minus e to the power minus into lambda 2 minus lambda 1 into t. So after that this will be outside and we get lambda 2 n2 by lambda 1 n1 is equals to lambda 2 by lambda 2 minus lambda 1 into 1 minus e to the power minus lambda 2 minus lambda 1 into t. This is equation 2. Because of lambda 2 is much greater than lambda 1, the lambda 2 by lambda 2 n2 by lambda 1 n1 is equals to lambda 2 by lambda 2 into 1 minus e to the power minus lambda 2 t. Okay, here lambda 1 becomes lambda 2 because of lambda 2 is much greater than lambda 1. So that after applicables long period of times e to the power minus lambda 2 t become negligible. So that lambda 1 n1 is equals to lambda 2 n2. In this case, parent nuclide essentially at same rate of as daughter nuclides. Okay, so this satisfying that secular or permanent equilibrium. So this graph shows the secular or permanent equilibriums. This line shows the daughter nuclei or the half-life of daughter nuclei, and this is half-life of parent nuclei. In this graph, you see the half-life of daughter nuclei is much smaller than half-life of parent nuclei because of it is disintegrating very fast, like 99%, 98%, 97%, 94%, and continuously it is reducing the daughter nuclei, the half-life of daughter nuclei with the respect of time. But the parent nuclei having half-life much greater. In a secular equilibrium, we will just studied the half-life of a parent nuclei is much greater than half-life of daughter nuclei. Like example, radium is parent nuclei and radon is daughter nuclei. The half-life of radium is approx 1600 years and the half-life of radon is approx 3.82 days. So we see that difference between the parent nuclei and daughter nuclei in a secular equilibrium. So third one or last one is transient equilibriums. The half-life of parent isotopes is greater than half-life of daughter isotopes. That means T1 is greater than T2, but not much greater than. Okay, so from equation 2 we have lambda 2 n2 by lambda 1 n1 is equals to lambda 2 by lambda 2 minus lambda 1 into 1 minus e to the power minus into lambda 2 minus lambda 1 into t. Since T1 is equals to 0.693 by lambda 1 and T2 is equals to 0.693 by lambda 2, that is for half life. Okay, so that lambda 2 n2 by lambda 1 n2 is equals to T2 by T1 minus T2 into 1 in minus e to the power minus lambda 2 minus lambda 1 into T. If T is very large, that means T is larger than T2 lambda 2 by T1 minus T2, so that lambda 2 n2 by lambda 1 n1 is equals to T2 by T1 minus T2. This is equation 3. And if it is clear that the for the large value of T, the ratio T2 by T1 minus T2 is greater than 1. This type of condition is called as transient equilibrium. So we will see this graph. So this line for the parent nuclei and this for the daughter nuclei. In this graph, we will see the half-life of parent nuclei is greater than the half-life of daughter nuclei, but not much greater than. Okay, so this type of equilibrium is transient equilibrium. Thank you so much for watching. We will see in the next interesting or important video. So keep watching.